Good afternoon, Chairman and members of the committee, as well as colleagues. Today I will present our collaborative research paper titled Video Verification Method of Evolution Model with Fractional Derivatives for Multi-Lane Traffic. The study represents a joint effort by our research group at MADI and P2C. It addresses a critical challenge in model intelligent transportation systems by uniting advanced computer vision architectures, long context deep learning models, and non-local fractional order continuum mechanics to establish safer, more stable urban freeway control networks. Let us begin with the core motivation behind the study. Modern intelligent transportation systems require highly precise real-time prediction frameworks to manage multi-lane freeway dynamics efficiently. However, severe nonlinear phenomena such as sudden stop-and-go waves and volatile line-changing patterns make traffic flow highly unpredictable. Traditional models face a critical trade-off. On one hand, integer-order continuum frameworks assume continuous, perfectly smooth traffic fields. When deployed on fractional road infrastructures, they fail due to massive numerical truncation errors. On the other hand, purely data-driven black box models, like long short-term memory networks, achieve strong tracking accuracy, but lack physical interpretability. Under critical boundary scenarios, these deep learning systems are prone to projecting anomalous physical dangerous acceleration commands. To resolve this conflict, we introduce a predictive corrective hybrid intelligence framework. This slide illustrates the structural pipeline of our hybrid intelligence model. The entire operational loop executes within a strict sliding 10-second observation window, updated continuously at each discrete interval of 0.1 seconds. The architecture consists of three distinct phases. In phase 1, our virtual detector systems VDS 2.0 analyzes raw digital video streams to extract real-time micro-scale variables, specifically traffic density, intensity, and velocity. In phase 2, these continuous parameters form a sequential state vector that feeds into a long context deep learning layer, combining bidirectional long short-term memory hidden passes and informer space self-attention blocks to predict an unconstrained candidate acceleration value. Finally, in phase 3, a deterministic supervisor monitors this candidate output. If an anomaly or high-risk state is detected, the supervisor mathematically intercepts the command and projects it into a convex safe set governed by a macroscopic SSSR micro framework, which is dynamically calibrated using fractional cross-lane viscosity constraints. Let us examine the data extraction core, which is our developed virtual detector system. Unlike conventional physical infrastructure tracking sensors like inductive loops, VDS 2.0 processes standard traffic closed-circuit television and internet video frames. The system inputs consist of full high-definition digitized frames recorded at 25 frames per second. To translate pixel movement into real-world metrics like meters or kilometers per hour, a 3x3 perspective homography matrix is computed using explicit structural roadway anchor nodes. Furthermore, to automatically position rectangular submatrices over non-linear lanes without manual intervention, a natural cubic spline interpolation routine calculates center lane paths. This allows the spatial matrices to map target roadway segments seamlessly. To successfully isolate moving vehicles matrices from static environments under volatile ambient lining condition, we apply strict multi-parametric filtering. Within each virtual detector matrix zone, parallel digital metrics are computed continuously. First, an L1 matrix norm quantifies the absolute pixel intensity average across the target domain. Second, a zone variance function evaluates inter-frame motion fluctuations relative to the preceding frame matrix to track spatial transients. Once these matrix sequences are normalized, the output profile is binarized into Boolean activation signals using a data-driven adaptive threshold parameter. An activation state of 1 signifies absolute vehicle occupancy, whereas an activation state of 0 denotes an empty roadway zone. Finally, consecutive premixity duration filters strip out environmental artifacts, shadows, and reflection noise, providing clean macro-parametric inputs for the next stages. We focus on how the binary activation signal form our virtual detectors are translated into traditional macroscopic hydrodynamic variables. This transformation is calculated over a calibrated spatial area. First, traffic flow intensity or vehicle throughput is quantified by scaling the total vehicle count over a designated time interval to hourly volumes. Second, the average velocity of the stream is evaluated by tracking the precise frame offset duration as the vehicle crosses from the initial entry boundary to the exit boundary of the zone. Third, traffic density is computed by determining the continuous spatial concentration of vehicles over the calibrated area. Finally, to make our framework adaptive, a real-time classification routine tracks individual pixel occupation lengths by evaluating data-driven frame occupancy intervals. The system automatically distinguishes between standard passenger cars and heavy trucks or buses. This categorical split allows us to adjust downstream microscopic safety margins in real time based on current traffic composition. Now, let us transition to the second major block of our architecture, which introduces the fractional continuum modeling network. As noted earlier, classical integer order hydrodynamic models assume that traffic fields remain perfectly continuous. However, under volatile highway transitions or near-structural road bottlenecks, traffic density and velocity profiles become non-differentiable, causing standard partial differential equations to break down. To capture these non-smooth multi-lane flows without artificial smoothness assumptions, we reformulate the continuity equation on contour sets. This is achieved by utilizing local fractional partial derivatives of order alpha, where alpha is bounded between 0 and 1. In this equation, ρ represents the fractional traffic density, while U and V defines the longitudinal and transverse velocity components. A major mathematical advantage of this approach is that truncating the local fractional Taylor expansion yields exactly zero truncation errors, isolating our control loop from the linear numerical anomalies common in traditional simulation. We extend this mathematical foundation to describe the dynamic evolution of the flow velocity over time. To account for internal shear stresses and the complex rheological properties of dense multi-lane traffic, the momentum equation is formulated using local fractional operation of order alpha. Here we change in velocity depends on traffic anticipation pressure, a relaxation time constraint, a longitudinal diffusion coefficient, and the local equilibrium velocity field. The most critical and novel addition is the term EL, which represents the cross-lane shear viscosity. The friction and collective drag generated when the vehicles execute lane change and maneuver cannot be modeled using classical derivatives because they exhibit non-local spatial history. Therefore, we structure this inner lane viscosity as a spatial fractional derivatives of order sigma. It is scaled by viscosity coefficient kappa, which mathematically dictates the velocity synchronization rate across agent multi-lane streams during intense maneuvering. While the full two-dimensional fractional hydrodynamic system is highly accurate, optimizing it directly within real-time control loops is computationally prohibitive. To resolve the operational challenge, we map the complex velocity perturbation dynamics onto an equivalent Begley-Torvik fractional oscillation model. In this formulation, the variable c represents the instantaneous lane mean velocity deviation from the local equilibrium velocity, while the Riemann-Liouville fractional derivatives tracks driver memory and hereditary lag. To calibrate this model, the structural parameters, including the system coefficient and the fraction order alpha, are dynamically identified in a MATLAB optimization environment. The system continuously minimizes a quadratic residual function between the theoretical trajectory and empirical time series data captured by our video analysis system over a sliding 10-second window. This optimization ensures that our mathematical model mirrors real highway physics at every moment. This slide establishes the vital mathematical bridge between our macro-scale continuum model and our micro-scale safety supervisor. To define strict boundaries for the vehicle tracking loop, we introduce small harmonic plane, wave perturbations around uniform traffic equilibrium state. The fundamental condition for asymptotic stability, meaning the successful attenuation of stop-and-go shock waves, mandates that the real part of the wave frequency must be less than or equal to zero. By solving this perturbation system, we derive an analytical stability bound structured as a strict inequality. This bound dictates what the equilibrium velocity derivative is strictly limited by the relaxation time, the longitudinal diffusion frequency, and the cross-lane shear viscosity parameters. This derived microscale criterion is exported directly to a deterministic supervisor, allowing the system to dynamically expand or contact individual vehicle safety buffers based on the surrounding fluid rheology. We look at the third major component of our architecture, the deep learning sequential forecasting loop. At each discrete interval, the localized multi-lane traffic state surrounding the target vehicle is captured within our sliding 10-second observation window. The state is formatted into empirical feature vector containing 6 key variables: the current space gap, the following vehicle's velocity, the leading vehicle's velocity, the relative velocity delta, the bounded time headway, and the clipped time to collision indicator. This dynamic feature sequence is then processed through a hybrid deep learning architecture designed to extract sequential variations and cross-lane dependencies simultaneously. First, a bidirectional long short-term memory network captures the chronological history of the hidden states. Next, these embeddings feed into an informer block equipped with probe-sparse self-attention layers to handle long context sequences efficiently. The final dense layer then projects this feature representation to output a raw, unconstrained candidate acceleration value. We explain how deterministic safety supervisor governed by the microscopic SSSR micro framework intercepts and corrects the neural network recommendations. The required spatial safety margin between vehicles is modeled as a quadratic function of the following vehicle's velocity. This margin depends on 3 critical parameters: the static jam gap, the driver reaction lag, and the effective mechanical braking performance. What makes our system unique is its dynamic parametric tuning. Instead of keeping these parameters fixed, our framework continuously updates them using the microscale fractional memory exponents and the cross-lane shear viscosity values derived from the continuum model. If severe stop-and-go instabilities occur, the supervisor automatically expands the safe microspace margin. To verify safety in real time, a binary anomaly predicate evaluates the future state. If executing the candidate neural acceleration would violate the boundaries of the safe state set, the predicate triggers an anomaly state of 1, alerting the system to intercept the command. This slide represents the numerical experiments and closed-loop validation results of our hybrid framework. To test the predictive corrective pipeline under rigorous real-world condition, we utilized high fidelity empirical vehicle trajectories from free standard open source databases. The HiD dataset, which features aerial drone footage of multi-lane freeways, the NGSIM dataset tracking intense transition stop-and-go traffic, and the Waymo autonomous vehicle trajectory dataset. The closed-loop performance synthesis proves what the exceptional reliability of our model. Across the three benchmarks, the safety metrics demonstrates a value of exactly 0.0 collisions. Even in complex scenarios where the black box neural network generates unsafe acceleration recommendations due to sequential anomalies, the corrective projection loop successfully intercepts the command and restricts it to a safe operational boundary, maintaining an optimal balance between tracking precision and physical safety. To better understand these results, let us examine the empirical statistical distributions illustrated on slide 14. Here we analyze the robust time to collision and longitudinal jerk metrics extracted from the NGSIM benchmark. The time to collision profiles confirm strict safety stabilization. Under our framework, the dangerous share of high-risk operational regimes, defined as time to collision of less than or equal to 1.5 seconds, converges strictly to zero. At the same time, we must ensure passengers' comfort. The longitudinal jerk distributions measured in meters per second cubed remain highly concentrated around zero. This statistical trend demonstrates that our safety constraints do not cause erratic vehicle behavior. Instead, they smooth outside transitions, proving that the supervisory loop effectively preserves acceptable driving comfort while guaranteeing absolute physical safety. This slide provides a concrete frame-by-frame look at a critical traffic event from the empirical dataset. The time series plots track vehicles pacing, speed tracking, acceleration profiles, and the corresponding time to collision metrics. As you can see in the speed and spacing graphs, pure neural tracking predictions frequently begin to drift and deviate from the physical ground truth during rapid multi-lane speed transitions. The acceleration plot perfectly illustrates our supervisor's interception mechanism. The moment the binary anomaly predicate detects a potential safety violation, the supervisor overrides the neural network. The section is visible as a sharp, discrete safety truncation pulses, dropping the acceleration down to a safe braking ceiling of minus 4.0 meters per second squared. This automated intervention forces the following vehicle to match the leader's velocity profile, stabilizing the time to collision metric and completely eliminating the collision vector. In conclusion, let us summarize the primary scientific and engineering contributions of this research. First, our predictive corrective architecture delivers guaranteed operational safety, achieving a collision rate of exactly 0.0 across high-density open-source highway benchmarks. Second, by introducing a two-dimensional fractional momentum framework, our model achieves high physical realism, successfully capturing non-local driver memory and cross-lane shear friction to accelerate stop-and-go wave damping. Third, the model serves as a practical tool for smart city infrastructure design, helping optimize signalized intersection intervals to maximize corridor throughput. Looking ahead, our future research will focus on two major areas. We plan to transition to variable order fraction derivatives, where the order parameter can adapt dynamically as a continuous function of local weather anomalies. Additionally, we aim to scale this projection framework to decentralized, multi-agent, cooperative vehicle-to-everything control architectures for large-scale urban networks. Here you can see some of our published works. Thank you very much for your attention.